A fence line of treated pine posts and plain wire runs across a flat red plain 560 kilometres north of Adelaide. The ground is red sand, loose gibberstones and low bluebush. Station tracks wind between dry watercourses that only carry water once or twice a decade. Pastoralists have run sheep and Hereford cattle over this patch of South Australian pastoral lease for generations, seeing only lean grazing country that required tens of thousands of hectares to support a modest herd. 350 metres beneath those cattle tracks lies one of the largest single concentrations of copper, gold and uranium ever recorded on the planet. For nearly a century of European settlement and mapping, geologists drove across this exact ground without stopping. The official geological maps published by the colonial and state mines departments showed only flat-lying, barren sedimentary rock extending across the Stuart Shelf. Every textbook rule of 20th century economic geology dictated that major metal deposits formed along volcanic island arcs or in folded mountain belts, where rock layers broke the surface and left gossans of oxidized iron for prospectors to chip with a hammer. Here, there was nothing to chip. The red sand gave away no geochemical scent, no magnetic needle swing on a surveyor's compass, and no mineralized rock outcrop across hundreds of square kilometres. How did a pastoral station in the arid interior of South Australia conceal a mineral deposit capable of redefining global commodity markets? And why did the science of the day insist it was impossible for anything to be there? For tens of thousands of years, Kokatha people and neighbouring First Nations groups moved through this country, living with an intricate knowledge of seasonal claypans, ephemeral salt lakes, and subterranean mound springs fed by the Great Artesian Basin. When pastoral leases were pegged out across the region in the late 19th century, including the remote pastoral property known as Roxby Downs Station, the focus of pastoralists was entirely on feed and bore water. The country was demanding, rainfall averaged less than 160 millimetres a year, and the ancient basement geology remained completely hidden beneath wind-blown sand, dune fields, and unmineralised shale. The geological consensus of the mid-20th century was entirely reasonable for its era. The Stuart Shelf, a broad tectonic platform on the eastern margin of the ancient Gawler Craton, appeared to be one of the most stable, inert geological regions on the continent. The surface layers consisted of Neoproterozoic sandstone and shale between 700 and 1,000 million years old. These flat-lying strata had not been subjected to the intense folding, faulting, or regional metamorphism typically associated with major base metal mineralisation. Every productive mining field in Australia at that time, the silver, lead and zinc lodes at Broken Hill, the copper deposits at Mount Isa, and the goldfields of Kalgoorlie had betrayed their presence at the surface through outcropping lodes discovered by foot prospectors. To drill blind through hundreds of metres of barren platform rock in the South Australian outback went against every economic and geological instinct. Yet in the late 1960s, the first conceptual cracks began to appear in that conventional thinking. At the Exploration Division of Western Mining Corporation in Melbourne, a small group of geoscientists led by Exploration Director Roy Woodall began to challenge the reliance on surface prospecting. They recognised that Australia's accessible outcropping deposits were largely exhausted and that the next generation of mineral discoveries would have to come from deep beneath barren sedimentary cover. The turning point emerged when geoscientist Douglas Haynes developed a radical theoretical model for sediment-hosted copper deposits. Haynes proposed that under specific chemical conditions, oxidizing groundwaters moving through continental basins could leach copper from deep basaltic lavas and transport it into overlying sedimentary traps. If the model was correct, giant copper systems could exist entirely concealed beneath younger, undisturbed rock platforms. The challenge was finding a way to see through the cover without drilling hundreds of speculative, expensive holes. The answer would come from the faint, invisible signals recorded on regional geophysical maps. The story behind this concealed wealth begins almost 1,600 million years ago during the Mesoproterozoic era. At that time, the Gawler Craton was not an arid plain, but a dynamic tectonic zone experiencing intense continental rifting and widespread magmatism. A massive thermal plume welled up beneath the crust, triggering the intrusion of the Hiltaba Sweet granites and the eruption of the vast Gawler Range volcanics across hundreds of square kilometres. Deep within this volcanic complex, a violent hydrothermal event occurred. High-temperature magmatic fluids, superheated and charged with fluorine, carbon dioxide, iron and rare earth elements, forced their way upward along major structural fracture zones. As these deep magmatic brines encountered cooler, oxidizing groundwaters circulating near the surface, A cataclysmic series of subterranean explosions shattered the surrounding granite. The result was a colossal hydrothermal breccia pipe, a funnel-shaped zone of fractured and crushed rock extending over an area roughly 7 kilometers long and 4 kilometers wide, plunging more than 1,000 meters into the crust. As the shattered rock settled into the crater-like collapse structure, iron-rich fluids precipitated hematite and magnetite on an enormous scale, creating a massive hematite-dominated breccia matrix. Interleaved with this dense iron core were rich concentrations of copper sulfides, predominantly chalcocite, bornite and chalcopyrite, alongside fine-grained native gold and significant quantities of uraninite, a primary uranium oxide mineral. This was not a standard sedimentary copper basin or a typical volcanic porphyry deposit. It represented an entirely unrecognized class of ore body, an iron oxide copper-gold deposit, now known universally by the geological acronym IOCG. Following this intense period of Mesoproterozoic volcanism and mineral precipitation, tectonic activity in the region subsided, and a long epoch of erosion and sedimentation took over. Over hundreds of millions of years, weathering stripped away the top layers of the volcanic pile, leveling the topography into a flat peneplain. Between 700 and 500 million years ago, during the Neoproterozoic and early Cambrian periods, the entire eastern flank of the Craton subsided beneath an ancient shallow sea. Layer upon layer of marine sediments settled across the eroded breccia complex, red-bed sandstones, conglomerates, and fine-grained shales of the Stuart Shelf sequence. These flat, unmineralized sedimentary strata formed an impermeable blanket between 300 and 350 meters thick. By the time modern European explorers crossed the region in the 19th century, including John McDouall Stuart on his expeditions north from Adelaide, every direct physical trace of the volcanic pipe was sealed beneath this sedimentary lid. The arid weathering of the Quaternary period completed the disguise, covering the bedrock with red sand dunes, silcrete cappings, and gibber flats. The deposit sat utterly silent, shielded from view, without a single outcropping rock to indicate that billions of dollars worth of copper, gold, and uranium lay directly below the station fences. For economic geologists in the 1970s, tracing a deposit buried beneath hundreds of meters of solid cover required looking beyond visible geology. It required instruments capable of sensing deep physical contrasts through the bedrock, variations in magnetic susceptibility, and differences in gravitational density. When geophysicists from Western Mining Corporation began cross-referencing regional gravity maps published by the South Australian Department of Mines with high-resolution airborne magnetic data, they noticed something extraordinary beneath the flat expanse of Roxby Downs Station. A massive, high-density gravity anomaly coincided almost exactly with a distinct magnetic high. The instruments indicated that an immense body of exceptionally dense, iron-rich rock was sitting directly beneath 350 meters of barren platform sediments. To confirm whether that dense subterranean mass held mere iron stone or a world-scale concentration of copper and uranium, the company had to take a high-stakes gamble and place a diamond drill rig on an unmarked patch of red sand. But when the first core barrel was hauled up to the surface in July 1975, the results would completely shatter existing geological theories. The scientific breakthrough that located Olympic Dam was an exercise in pure geophysics and spatial analysis, executed at a time when blind, deep drilling undercover was considered an unjustifiable commercial risk. In May 1975, Western Mining Corporation exploration geophysicist Hugh Rutter took the regional gravity survey data gathered by the South Australian Department of Mines and combined it with low-level aeromagnetic survey lines flown across the Stuart Shelf. What Rutter identified was a target coded as RD1, a coincident gravity and magnetic anomaly of exceptional amplitude. The gravity signature indicated an enormous mass of dense rock sitting beneath the barren platform, while the magnetic data suggested that this high-density body contained significant quantities of iron oxides. On the 12th of June 1975, a drilling rig operated by contract drillers began sinking diamond drill hole RD1 on an unmarked section of pastoral lease on Roxby Downs Station. For the first 335 meters, the core barrel returned exactly what the regional geological maps predicted: flat, unmineralized Neoproterozoic quartzite and sandstone, followed by the red mudstones of the Arcuna quartzite and the Corroborra sandstone. There was no trace of copper, no altered rock, and no structural disturbance. Then, at a depth of 353 meters, the drill bit cut directly across an unconformity into intensely altered, hematite-rich breccia. The laboratory assays of that first hole, completed in July 1975, confirmed an intersection of 38 meters, averaging 1.05% copper. The mineralisation sat inside a dense, dark red matrix dominated by finely ground hematite, laced with grains of chalcocite, bornite, and chalcopyrite. Yet the true scale of the system did not reveal itself immediately. The next 8 drill holes, drilled across a wide grid over the subsequent 12 months, yielded mixed and largely sub-economic results, creating severe doubts among management about whether the discovery was merely an isolated pod of alteration. The decisive turning point arrived in November 1976 with the drilling of diamond drill hole RD9. Located roughly 1 kilometre from the original discovery hole, RD9 intersected 338 metres of continuous mineralisation averaging 2.1% copper. More critically, radiometric logging and multi-element geochemical assays of the RD9 core revealed something entirely unexpected: high concentrations of uranium oxide sitting alongside significant quantities of native gold and silver. The scientific team, which included project geologist Douglas Haynes and petrologist Jim Layler, realized they were looking at a rock system that defied every established classification in economic geology. The ore was not confined to a single bedding plane or structural vein. It formed a vast, interconnected breccia complex spanning several square kilometers. To map the full geometry of the deposit without drilling thousands of blind holes through solid rock, the team deployed high-resolution ground gravity surveys, dipole-dipole induced polarization surveys, and downhole geophysical logging. Over subsequent years, geochronologists using uranium-lead zircon dating at the Australian National University determined that the host breccias and granites formed approximately 1,590 million years ago. The scientific verification was absolute. Olympic Dam was not an anomaly within an existing deposit model, but the founding type example of a completely new geological category. Yet proving the existence of an immense subterranean mineral system 350 metres beneath the South Australian desert was only the first hurdle. Transforming a remote geophysical target into the largest underground mine in the Southern Hemisphere would require engineering feats and legal frameworks that would permanently alter the state's economic and political landscape. The transformation of an invisible anomaly beneath red sand into an industrial complex required the construction of a purpose-built town, a dedicated water pipeline, and an entirely new legal framework. In 1982, the Parliament of South Australia passed the Roxby Downs Indenture Ratification Act, granting the operating joint venture long-term certainty over mineral leases, water access, and infrastructure development. 6 years later, in 1988, commercial production commenced under the operation of Western Mining Corporation, which was subsequently acquired by BHP in 2005 for $7.3 billion. Today, Olympic Dam represents one of the most substantial mineral resources on Earth. According to formal resource statements published by BHP, the total mineral resource exceeds 9,000 million tonnes of ore. This includes an estimated 78 million tonnes of contained copper, more than 2 million tonnes of uranium oxide, and roughly 2,500 tonnes of gold. To extract these commodities, miners work within a subterranean road network spanning more than 1,000 kilometres of underground tunnels, descending beyond 800 metres beneath the desert surface. The mine produces roughly 200,000 tonnes of refined copper cathode, 4,000 tonnes of uranium oxide concentrate, and over 100,000 ounces of gold annually. Yet operating a world-scale mineral processing facility in an arid environment creates severe, continuous demands on regional hydrology. Olympic Dam consumes approximately 35 megalitres of water every day. This water is drawn from Wellfield A and Wellfield B, located over 100 kilometres to the north in the Great Artesian Basin, and transported via buried pipelines. This extraction remains a point of continuous scientific and environmental scrutiny. Hydrogeological monitoring by the South Australian Department for Environment and Water tracks pressure drops across the artesian aquifer to ensure the preservation of fragile mound springs, vital endemic ecosystems that Kokatha and Arabana traditional owners have protected for thousands of years. The human footprint on the surface is defined by the township of Roxby Downs, situated 16 kilometres south of the mine. Established in 1988, the town has a permanent population of roughly 4,000 residents, making it the primary service hub in the region. The presence of the mine fundamentally shifted the economic geography of South Australia. Olympic Dam accounts for a substantial proportion of the state's total mineral exports and provides thousands of direct and indirect jobs across metallurgical processing, heavy haulage, and specialized drilling. However, the immense scale of the deposit introduces enduring technical and economic questions. Despite decades of continuous mining, less than 10% of the total resource has been extracted. The challenge lies in the deep underground access methods, the metallurgical complexity of separating finely disseminated uranium and rare earths from copper sulfides, and the volatile economics of global energy transition metals. The sheer volume of mineralisation sitting sealed beneath the Stuart Shelf reshaped not only modern mining engineering, but our entire understanding of how ancient continents hide their wealth. What remains to be confronted is what this single, hidden system reveals about the rest of the Australian landmass. The discovery at Olympic Dam did not just create a single giant mine, it completely opened a vast search corridor across the eastern Gawler Craton. Once geologists understood what the geophysical signature meant, exploration crews returned to other unexplained gravity highs that had sat uninvestigated on government surveys for decades. That systematic re-examination led directly to the identification of other major concealed deposits across the region. Prominent Hill, located 130 kilometres southeast of Coober Pedy, discovered in 2001 beneath 100 metres of cover. Karapatina, situated 100 kilometres south of Olympic Dam, discovered in 2005 under 470 metres of barren sedimentary rock. And Oak Dam West, where deep diamond drilling in 2018 confirmed intense hematite-hosted copper mineralisation at depths exceeding 800 metres. Each of these systems was entirely invisible at the surface. Each was found using the exact methodology pioneered at Roxby Downs. What kept Olympic Dam and its sister deposits hidden for so long was not their depth, but the dogmatic assumption that a mineral deposit had to show itself at the surface before it was worth drilling. For nearly a century, exploration had treated the flat-lying cover of the Australian continent as the end of the geological story, rather than a thin veil over an ancient, highly mineralised basement. The moment that conceptual blind spot dissolved, the Stuart Shelf was transformed from an inert sedimentary desert into the centre of one of the richest copper-uranium provinces in the world. Yet significant geological and environmental unknowns remain active today. Geoscience Australia and the Geological Survey of South Australia continue to map the deep lithospheric architecture of the Gawler Craton using broadband magnetotellurics and deep seismic reflection traverses, trying to determine why these massive magmatic fluid systems localized along specific structural corridors while bypassing others. At the surface, the long-term impact on the Great Artesian Basin continues to be measured millimetre by millimetre at ancient desert mound springs, where the delicate balance between industrial extraction and groundwater recharge remains an open, unresolved question. Look across that stretch of red plain north of Port Augusta today. The same blue bush grows across the sand. The same fence lines run to the horizon under a pale sky. The published topographic map shows an orderly grid of pastoral blocks, names of dry creeks, and a few sealed roads, neat and apparently complete. The map looks finished. The ground beneath it is not. Which feature or anomaly in your own state or territory has always struck you as out of place, or went unnoticed for generations before someone looked beneath the surface? Drop your thoughts in the comments and subscribe to keep uncovering what lies hidden across the landscape.